For years, the interface for artificial intelligence has been a single pulsing cursor. We treated these models like highly advanced typewriters, operating under the assumption that if we just found the perfect string of magic words, we could guarantee a perfect result. But as tasks grow in complexity, this reliance on phrasing becomes a bottleneck. A prompt is a static input, and in a probabilistic system, static inputs produce inconsistent, unpredictable outcomes. This inconsistency is driving a shift toward context design. Success no longer depends on the question itself, but on the structural environment constructed around the model before the first character is even typed. Market analysis from Gartner and Forrester highlights this transition, with 70% of enterprise implementations moving away from manual prompting and toward automated context systems. This shift is a response to a mathematical reality. An LLM operating in isolation has no anchor. Without specific external constraints, the model relies solely on its next token prediction, which leads directly to hallucinations and generic approximations. Reliability requires a dynamic environment. The model must be integrated with external databases, live APIs, and a persistent memory of previous interactions to remain grounded in fact. We are moving past the era of the writer coaxing an output. We are entering the era of the architect, engineering deterministic systems that force a model into precision. Effective design begins by identifying the anti-prompt, the specific input patterns that cause a system to fail. These typically manifest as either the information dump or the vague request. The information dump overloads a prompt with conflicting data points, fracturing the output's logic. Conversely, the vague request provides too little data, defaulting to common training data and resulting in a blurry, generic output. Both failures ignore the system prompt, the primary layer of hidden rules that govern a model's base behavior. If these hidden instructions aren't specifically overridden or aligned with the user's goals, the model defaults to its baseline programming, often ignoring the very constraints the user is trying to apply. Without an architectural framework to manage these variables, the user has no systematic control over the technical execution of the task. To gain that control, we apply structural upgrades to the context. The first is few-shot prompting. Few-shot prompting injects 3 to 5 flawless examples of a desired output into the model's immediate context. This provides a rigid pattern to follow, accurately replicating specific brand voices or complex data structures without lengthy descriptions. A more advanced constraint is chain-of-thought prompting, which targets the model's logical processing. Chain of thought forces the model to generate intermediate reasoning steps. It must articulate its logic before it is allowed to predict the final conclusion. This is a mathematical necessity for complex tasks. By breaking a problem into discrete steps, the model avoids the logic collapse often seen in one-shot mathematical or coding requests. Showing the work reduces the probability of a stochastic hallucination. If the model is forced to follow a verifiable logical pathway, the output becomes predictable. These constraints transform the interaction from a game of chance into a controlled logic engine. We further expand this architecture through multimodal prompting, which allows the system to ingest visual and spatial information. For example, a model can analyze a hand-drawn whiteboard sketch and map its components into precise digital coordinates. It then translates that visual data directly into functional, production-ready code, effectively reading the intent of the drawing. For data fidelity, the industry standard is RAG, Retrieval Augmented Generation. RAG attaches external proprietary knowledge bases directly to the model's context. This allows the system to reference current, verified data rather than relying on frozen knowledge from its initial training. Integrating multimodal vision and RAG memory provides the model with a live, verified environment for its operations. The final phase of this architecture moves into agentic autonomy, where the system manages its own execution loops. An autonomous generation node produces an initial draft. This output is passed to a second node, an automated critic that highlights structural flaws. A third node then rewrites the output based on that critique, correcting errors before a human ever sees it. By automating the feedback loop, we remove the need for repetitive human trial and error. These workflows allow AI systems to systematically verify their own logic, providing a level of autonomy that static prompts cannot achieve. This complete architecture, integrating RAG, logical constraints, and agentic loops, defines the modern landscape of AI. This structural shift has changed the professional requirements for those working with these models. While the standalone title of prompt engineer has become less common, the underlying skill set of context design is now a mandatory requirement across technical and creative fields. Experts capable of managing these autonomous agentic systems are seeing significant market demand, with compensation reaching up to $250,000. This value is generated because context designers translate abstract business goals into the specific technical environments that produce flawless execution. Precision in language and the ability to design logical systems are now the primary bottlenecks in AI implementation, far outweighing the need for manual coding. A structural context loop automates the iterative process of prompting, critiquing, and revising, replacing hours of manual human refinement with a single engineered system.